Hello friends, welcome you all in my YouTube channel. This is Mr. DM Sirsat, Assistant Professor, Department of Chemistry, Anandibai Raurani Arts, Commerce and Science College, Vaibhavadi. Friends, today we are going to discuss the structure elucidation by using spectral data. Means simply by using UV, IR and NMR data to find out the structural formula of any organic molecule. Okay. Next, the contents of my presentation, some important absorption values of UV spectroscopy, some important absorption values of IR spectroscopy, some important values of H1NMR spectroscopy, and then some selected problems. Friends, before starting the problems, it is very important to know the significant values, significant absorption values of UV, IR as well as H1NMR spectroscopy. Let's say one by one. Number one, important values of UV spectroscopy means important absorption values of UV spectroscopy. This is the compounds and this is the lambda max value. See the number one example, ethene molecule. Ethene molecule having lambda max value is 175 nanometer. But same number second is a butadiene molecule. Butadiene molecule means conjugation increases. Basically UV spectroscopy is used to determine the extended conjugation. Ethene and butadiene, in case of butadiene, conjugation increases automatically, the lambda max value also increases, and the lambda max value of this butadiene molecule is 217 nanometer. Then acrolein molecule, it is a simple unsaturated aldehyde having lambda max value 210 nanometer. Styrene molecule, styrene means one ethene unit is directly bonded with the benzene, means there is a strong conjugation having lambda max value is 214. Then acetophenone is the aromatic nucleus, is the aromatic ketone having lambda max value is 240 nanometer, and these are the simple name of molecules and their lambda max values. Then again phenol, benzaldehyde molecule, nitroaniline molecule, nitroaniline molecule, para-nitroaniline molecule. See, these are the three examples. In case of orthonitroaniline molecule, the lambda max value is 222 nanometer, and is a meta-nitroaniline, it is a lambda max value is 235 nanometer, and is a para-nitroaniline having lambda max value is 229. Means the conjugation increases, then lambda max value also increases. The last one example, the stilbene, the trans stilbene, and number second is the cis stilbene. The trans stilbene having lambda max value is 295 nanometer, and the cis stilbene having lambda max value is 280 nanometer. Means by using UV spectroscopy we can identify the isomerism, means either this isomer is a cis or trans. Okay. The next one is the important absorption values of IR spectroscopy. These are the bond, means basically IR spectroscopy is used to determine the functional group of any organic molecule. See one by one, these are the simple the stretching frequency of carbon and hydrogen, but the nature of carbon is sp3 hybridized carbon, means alkane molecule having absorption value is 2850 to 2960 centimeter inverse. Okay. Number second is alkene molecule, means the stretching frequency between this carbon and hydrogen. The nature of this carbon is sp2 hybridized carbon. As sp2 hybridized carbon is a more electronegative, means the stretching frequency of this carbon and hydrogen is 3010 to 3100 centimeter inverse. Then number third, alkyne molecule, again same stretching frequency of carbon and hydrogen, but nature of carbon is sp hybridized. So basically sp is more electronegative than sp2 is more electronegative than sp3 hybridization. Is a more electronegative carbon, means the carbon hydrogen bond is more stronger having stretching frequency is a 3300 centimeter inverse, means hybridization increases automatically, the absorption frequency in IR spectra also increases. Then next example is a stretching frequency of carbon and hydrogen in aromatics, means suppose consider the example benzene. In case of benzene, the stretching frequency of carbon and hydrogen is a stretching frequency is 300, means 3000 to 3100 centimeter inverse. In case of aldehyde molecule, the stretching frequency of carbon and hydrogen the same 2650 to 2880 centimeter inverse. The stretching frequency of carbonyl group, basically carbonyl group is present in number one aldehyde ketone, means CO group present in aldehyde, ketone, acid and their derivatives. Their derivatives means ester molecule, anhydride molecule, acid chloride molecule, amide molecule, and this all stretching frequency of all groups, it in the range of between 1680 centimeter inverse to 1760 centimeter inverse. Then stretching frequency of OH means oxygen and hydrogen, it is a simple 3600 to 3650 centimeter inverse. But this OH group is monomeric, means there is no hydrogen bonding. In case of hydrogen bonding, the stretching frequency is 3200 to 3400 centimeter inverse. The next one is the stretching frequency between this carbon and carbon. In case of aromatic nucleus, the stretching frequency is 1500 to 1600 centimeter inverse. The stretching frequency of NH bond, nitrogen and hydrogen in amines, is a 3300 to 3500 centimeter inverse. The stretching frequency of carbon single bond nitrogen in case of amines is 1180 to 1360 centimeter inverse. The stretching frequency of nitrite means C triple bond N, both carbon as well as nitrogen, both are sp hybridized. Is more sp hybridized means the bond between carbon and nitrogen is a stronger bond, having absorption value is 2210 to 2260 centimeter inverse. The stretching frequency of this NO group, it is a simple 1330 to 1540 centimeter inverse. See, this is the one by one. It is a simple the stretching frequency of hydroxy group, stretching frequency of C triple bond C, then stretching frequency of C double bond C in case of alkenes, C double bond C in case of aromatics, it shows absorption 1500 to 1600, but in case of alkene molecule, it gives absorption 1620 to 1680 centimeter inverse. And in case of alkane means carbon bond stretching frequency, CC bond stretching frequency in alkanes, it is a 600 to 1500 centimeter inverse. And in case of IR spectroscopy, there is some bending vibrations. Then next one, it is the important values of H1 NMR spectroscopy. Basically, the H1 NMR spectroscopy means proton nuclear magnetic resonance spectroscopy is used to determine the nature of hydrogen as well as number of hydrogen in the particular molecule. See, one by one, this simply alkane molecule means this 3 hydrogen directly bonded with carbon. Carbon is sp3 hybridized. It gives absorption. So approximate delta value of this hydrogen is 0.9 ppm. But same alkane molecule, same hydrogen, but nature of carbon is a primary carbon, secondary carbon and tertiary carbon. In case of primary carbon, the delta value is 0.9 ppm. In case of secondary carbon, delta value is 1.3 ppm is approximate value. In case of tertiary, the delta value is 1.4 ppm. See, this is a simple methyl group is directly bonded to carbonyl. Is the nature of this carbonyl group, it acts as electron withdrawing group. It withdraws electron from this adjacent methyl group, means electron density of this carbon decreases, means delta value increases, and this proton it gives signal is in the range of 2.1 ppm. Next one is a hydrogen with a triple bonded carbon. The nature of this carbon is sp hybridized, is more electronegative. Then again it is in the downfield region, it gives signal at a approximate value is a 2.5 ppm. Then CS2 means these 2 hydrogen and there is one X group. X is either halogen or oxygen. Halogen as well as oxygen, these are the more electronegative, and due to the more electronegative nature of this X group, electron withdraw from this CS2 means electron density decreases automatically. The delta value also decreases. It means it gives signal in the downfield region and the delta value is 3 to 4 ppm. Then hydrogen which is directly bonded to double bonded carbon, means these are the simple C double bond C and hydrogen, it gives signal to 5 to 6 ppm due to anisotropic effect. It is a simple definition of anisotropic effect is a structure dependent shielding and deshielding is called as anisotropic effect. Okay, due to anisotropic effect, this proton of alkene it gives signal at 5 to 6 ppm. It's the same, it gives 1.7 ppm, means this carbon is a highly shielded zone. This proton which is directly bonded to this double bonded carbon, it gives delta value, it gives signal in the range of 5 to 6, and this CS3 group it gives signal in the 1.7 ppm. Then protons of aromatic nucleus it gives signal 7 to 7.2 ppm. Then CH3 group is a 2.3 ppm. Basically this methyl group, nature of carbon is primary carbon, but this methyl group is directly bonded to this phenyl nucleus, and the phenyl nucleus is more electronegative, and due to electronegative nature it gives signal at downfield region comparative to this methyl group. This methyl group, it gives signal 0.9 ppm, but same methyl group which is directly bonded to phenyl nucleus, it gives signal at 2.3 ppm. Then aldehydic proton, it gives signal at 9 to 10 ppm, means it's a simple anisotropic effect. Then next one is acid. Acid again it gives signal 10 to 12 ppm. Then alcohol is a phenol, and amine molecule, it gives signal in the corresponding level, means 2 to 5, 4 to 7, and 5 to 1.5 to 4 ppm. These are the important values of H1 NMR spectroscopy. Next one, it is a simple representation, means saturated molecule, it gives signal from 0 to 1.5 ppm, and these are the allylic molecule, it gives signal in the 1.5 to 2.5 ppm. Then this carbon is again directly bonded to Z group. Z is either oxygen, nitrogen, halogen, means there is a more electronegative group, means electron density of this carbon decreases, means it gives signal in the range of 2.5 to 4.5 ppm. Then phenylic proton, it gives signal in the 4.5 to 6.5 ppm. Then aromatic proton, means this hydrogen which is directly bonded to ring carbon, there is a basically this carbon is sp2 hybridized, as well as there is a ring current, and due to this, and main important factor is that there is an anisotropic effect, and due to anisotropic effect this proton, it gives signal in the 6.5 to 8.0 ppm, and the last one is aldehyde and acid, it gives signal in 9.0 to 12 ppm. These are the some important values of UV spectroscopy, then IR spectroscopy, and next one is the H1 NMR spectroscopy. Let's see one by one problems. Okay, the problems of structure elucidation by using spectral data. Friends, basically for solving the problem, first important step is to find out the index of hydrogen deficiency, means simply to find out the unsaturation. The unsaturation is calculated by using simple formula 2x plus 2 minus y divided by 2, where x is equal to number of carbon, where y is equal to number of hydrogen. Okay, in case of halogens, means fluorine, chlorine, bromine or iodine, the symbol is replaced by one hydrogen. In case of nitrogen, each nitrogen is replaced by one CH unit, means there is one carbon and one hydrogen. Okay, what is mean by index of hydrogen deficiency? So basically when the molecule has no double bond or ring, there is a 0 index of hydrogen deficiency. When the molecule has one double bond or one ring, its hydrogen deficiency is 1. For triple bond, the hydrogen deficiency is 2, and for ring, the hydrogen deficiency is 1, and is calculated by using simple formula is again 2x plus 2 minus y divided by 2, where x is equal to number of carbon and y is equal to number of hydrogen. Okay, these are the first key, is the first important step before solving the spectroscopic problem. Okay, let's see one by one. Number one problem, see a compound having molecular formula C4H10O having spectral data. The spectral data, IR spectral data, it gives two signals. Number one, 3500 centimeter inverse to 3350 centimeter inverse is the number first signal, and number second is 1100 centimeter inverse. It is NMR data, H1 NMR data. It gives two signals. Number one is 1.1 ppm, delta is equal to 1.1 ppm. It is 9H singlet, and the number second signal is delta is equal to 3.2 ppm, 1H broad singlet, and this singlet, this peak is a D2O exchangeable. Okay, then solve this problem. Number first important step is to find out the index of hydrogen deficiency. The index of hydrogen deficiency 2x plus 2 minus y divided by 2, where x is equal to number of carbon. In this molecular formula, the number of carbon is 4 and y is equal to number of hydrogen. Number of hydrogen is 10, means 2 into 4 plus 2 minus 10 divided by 2, answer is 0. Means 2 into 4, 8, 2 minus 10 means again 8, 8 minus 8, 0. The final answer is 0, means there is a no index of hydrogen deficiency, means there is a no any ring, there is a no any unsaturation. Okay, then from IR data, the IR data means it gives two peaks. Number first peak, absorption between 3500 to 3350 centimeter inverse, it indicate means there is a OH group, means it gives signal due to this OH stretching, and is a hydrogen of this hydroxy group. OH group is a D2O exchangeable. Number second is absorption at 1100 centimeter inverse is due to carbon single bond oxygen stretching. Carbon single bond oxygen stretching. Okay, from NMR data, in NMR there is a two signals. Number first signal, singlet at 1.1 ppm from 9 hydrogen indicates there is a 3 methyl group, means these 3 methyl groups are equivalent, and this 3 equivalent methyl group means 9 proton, it gives one signal, means sharp singlet, means the singlet at 1.1 ppm at of 9H indicate the 3 methyl group attached to only one tertiary carbon, only one tertiary carbon. And the number second is a broad singlet at 3.2 ppm, which is D2O exchangeable, indicate there is a hydrogen of hydroxy group, the hydrogen of hydroxy group, OH group. And so from above data, it is a probable structure, means final structure of this compound, the molecular formula C4H10O is a simple tertiary butyl alcohol. See, this is the tertiary carbon that directly bonded to number 1 methyl group, second methyl group, tertiary methyl group, and there is one hydroxy group. The first, second and three methyl group means there is a 9 protons, 9 hydrogens. These 9 protons are equivalent, and this 9 proton, it gives only one sharp singlet at 1.1 ppm. And number second, this proton means there is a no adjacent proton, means there is a no splitting. It is a proton of this hydroxy group, OH group, again there is a no splitting pattern, means it gives one sharp broad singlet at 3.2 ppm. The broad due to their exchangeable nature, and this hydrogen is exchangeable with deuterated water. These are the number first problem. Next, see the number second problem. The number second problem is a compound having molecular formula C4H8O and spectral data, it gives only one significant absorption in IR spectra at a 1740 centimeter inverse. And number second, H1 NMR data, it gives 3 signal in the NMR. Number first, delta is equal to 1.1 ppm, 6H doublet. Number second, delta is equal to 2.3 ppm, 1H multiplet, and delta is equal to 9.4 ppm, 1H doublet. Okay, start the find out the structure of this molecule. Simply, firstly find out the index of hydrogen deficiency. The simple formula 2x plus 2 minus y divided by 2. Again, number of carbon 4, number of hydrogen 8. The 2 into 4 plus 2 minus 8 divided by 2 means hydrogen deficiency is 1. 2 into 4, 8 minus 6 divided by 2, answer 2 by 2 means there is answer 1, means hydrogen deficiency is 1, means there is a either one ring, there is either one double bond. These are the index of hydrogen deficiency. Okay, from IR spectrum, in IR spectra there is only one significant absorption at 1740 centimeter inverse. So basically the absorption at 1740 centimeter inverse is due to presence of C double bond O. C double bond O is a aldehydic C double bond O, means there is a presence of aldehyde functional group. Number second, from H1 NMR data, in H1 NMR there is a 3 signals. Number 1 is a 1.1 ppm, is a doublet at 1.1 ppm of 6H, indicate there is a 2 methyl group, means 1 methyl group 3 proton, second methyl group 3 proton. These 6 protons, these are the equivalent in nature, and this 6 proton, it gives one doublet, means this 2 methyl group which is directly bonded to one CH unit, means this 2 methyl group which is directly bonded to CH unit, and in NMR spectrum, the splitting pattern is according to n plus 1 rule. N is equal to number of proton to adjacent carbon. Means suppose this 2 methyl group directly bonded to this CH, then the adjacent proton is only 1, means according to splitting pattern n plus 1, 1 plus 1 is equal to 2, means this 2 methyl group, it gives doublet at 1.1 ppm. Then multiplet at 2.3 ppm of 1H indicate the CH group attached to 2 methyl group, means 2 methyl group means more than 5 adjacent proton. So basically this CH unit is directly bonded to 2 methyl group, the number of proton is a 6 plus 1 7 means is a multiplet, means multiplet at 2.3 is due to presence of the CH means which is directly bonded to 2 methyl group. And the last signal, the doublet at 9.4 ppm of 1H indicate there is a aldehydic proton. See, from above data, the structure of molecule is a simple CS3CH, CS3, C double bond OH. Okay. See the IR data, IR spectroscopy. In IR data, it gives only one significant absorption at 1740 centimeter inverse is due to presence of the C double bond O. Number 1, in H1 NMR spectroscopy, it gives one significant absorption at 1.1 ppm. 6H means this 2 methyl group, 1 methyl group, 2 methyl group, this 2 methyl group directly bonded to 1 CH, means these two are equivalent, and the 6 proton splitted this adjacent CH, means adjacent 1 proton, and it gives doublet, and this 1 hydrogen it split to this 2 methyl group as well as this 1 adjacent hydrogen, and it gives multiplet, and this aldehydic proton it gives signal at 9.4, means it splitted to this adjacent CH, means it gives doublet, means there is a doublet of this 2 methyl group, multiplet of this CH, and is a doublet of this aldehydic proton. These are the problem number 2nd. Then problem number 3rd, see, it is a simple, a compound having molecular formula C8H8O having spectral data, it gives signal in IR spectra at 1690 centimeter inverse, 1470 centimeter inverse, 1370 centimeter inverse, 2890 centimeter inverse, and the last these two bending vibrations means 750 centimeter inverse and 690 centimeter inverse. Again in NMR spectrum, it gives two significant peak. Number 1, delta is equal to 2.1 ppm of 3 proton singlet, and delta is equal to 6.9 ppm 5 proton multiplet. See one by one. First calculate the index of hydrogen deficiency. Here number of carbon 8, again number of hydrogen 8, means 2 into 8 plus 2 minus 8 divided by 2, 2 into 8 16 plus 2 minus 8 means 16 minus 6 divided by 2 means 10 by 2 is equal to 5, means there is a 5 index of hydrogen deficiency. Okay, see one by one. From IR data, in IR it gives significant absorption at 1690 centimeter inverse. See, absorption at 1690 centimeter inverse is due to presence of C double bond O stretching. The C double bond O stretching, the stretching frequency of carbonyl in the range between 1690 centimeter inverse to 1845 centimeter inverse. Number 2nd, absorption at 1470 centimeter inverse is due to presence of C double bond C, means C double bond C, there is a 2 types of C double bond C, is the aromatic and number 2nd is the aliphatic, and this stretching frequency is due to presence of aromatic C double bond C stretching. Okay, absorption at 1370 centimeter inverse is due to presence of carbon single bond carbon stretching. Then absorption at 2890 centimeter inverse is due to CH stretching of methyl group. See, the carbon and hydrogen, the stretching frequency between this carbon and hydrogen, it gives significant absorption in the range of 2800 centimeter inverse to 3000 centimeter inverse, and in this it gives one significant absorption at 2890 centimeter inverse due to presence of this methyl group CS stretching, and last one is absorption 2 bands at 750 and 690 centimeter inverse is due to mono substituted benzene. Then see the H1 NMR data. In an H1 NMR data, it gives two signals. Delta is equal to 2.1 ppm due to presence of 3 hydrogens, and is a 6.9 ppm due to presence of 5 hydrogen. It gives multiplet, and this 3 proton it gives singlet. Singlet at 2.1 ppm of 3 proton indicate there is a methyl group, and this methyl group is directly bonded to more electronegative atom, either carbon or oxygen. See, this methyl group is directly bonded to sp2 hybridized carbon. Then this absorption means delta value of this proton, it decreases from 0.9 to 2.1 or 2.5. Then multiplet at 6.9 ppm of 5H indicate the aromatic protons. And from above data, the structure of this molecule C8H8O is a simply acetophenone. See one by one. In IR spectroscopy, it gives one significant absorption at 1690 centimeter inverse due to presence of CO. Basically carbon double bond oxygen, it gives absorption at 1690 centimeter inverse, and this value decreases due to presence of this methyl group. According to inductive effect, this methyl group it acts as electron donor. When methyl group donate electron to this carbonyl carbon, then stretching frequency means the stretching frequency of this carbon and oxygen decreases, means it gives signal at 1690 centimeter inverse. It is a significant absorption at 2890 centimeter inverse due to presence of this methyl group carbon hydrogen stretching, and is a C double bond C means 1470 centimeter inverse is due to ring C double bond C stretching. And in case of this NMR, there is a two signal. Number one signal singlet at 2.1 means this methyl group there is no adjacent proton, and according to splitting pattern n plus 1 means n plus n is equal to 0 means 0 plus 1 is again 1 means it gives one singlet at 2.1 ppm, and this 5 proton it gives multiplet. This 5 aromatic protons it gives multiplet. These are the problem number 3rd. Then number 4th problem, see a compound having molecular formula C7H7NO2. C7H7NO2 having spectral data. Number 1 IR spectral data, it gives number first signal in the range of 3000 to 3100 centimeter inverse. Number second 2850 to 2950 centimeter inverse. Number third 1500 to 1600 centimeter inverse, and number 4 1330 to 1540 centimeter inverse. In case of H1 NMR, again it gives number 1, 2 and 3 signals. Number first signal at 2.4 ppm due to presence of 3 hydrogen singlet. Number second 7.4 ppm 2H doublet, and number third 8.2 ppm 2H doublet. Okay, just let's see one by one. First calculate the index of hydrogen deficiency according to same formula is 2x plus 2 minus y divided by 2. Here number of carbon 7, number of hydrogen 7, but there is one nitrogen, and for nitrogen is replaced by one CH unit, means there is a number of carbon, consider number of carbon 8 as well as number of hydrogen 8, means 2 into 8 plus 2 minus 8 divided by 2, final answer 5, means there is a 5 unsaturation. From IR data, in IR it gives number first significant peak, means absorption at 3000 to 3100 centimeter inverse is due to presence of aromatic CS stretching, means there is a aromatic carbon and hydrogen stretching frequency in the range of 3000 to 3100 centimeter inverse. Number second, absorption at 2850 to 2950 centimeter inverse is due to presence of CS stretching, but CS stretching is aliphatic, means there is a presence of methyl group. Number third, absorption at 1500 to 1600 centimeter inverse is due to presence of aromatic carbon double bond carbon stretching, and is a absorption at 1330 to 1540 centimeter inverse is due to presence of NO2 group. See the NMR data. In NMR, singlet at 2.4 ppm of 3 hydrogen means there is a methyl group, and this methyl group means is directly bonded to more electronegative atom. Means this when methyl group is directly bonded to more electronegative atom, means electron density of this methyl group decreases automatically, the delta value also increases, means it gives signal at the downfield region. Number second, doublet at 7.4 ppm. Basically the 7.4 ppm and 8.2 ppm means there is a aromatic ring. The doublet at 7.4 ppm of 2H indicate the aromatic protons. Indicate the aromatic protons. It is the number third signal. Doublet at 8.2 ppm of 2 hydrogen indicate the aromatic proton, means there is a 4 aromatic proton. It is confirmed that there is a bi-substituted molecule, and in IR spectra it gives two significant peak. Number first is a 2850 to 2950 centimeter inverse is due to presence of aliphatic CS stretching, and last is the absorption at 1330 to 1540 is due to presence of nitro group. There means there is a bi-substituted aromatic nucleus, bi-substituted benzene, and these substitutions are number one methyl group and number second is a nitro group, and these two groups are para to each other. Means this methyl group it gives singlet at 2.4 ppm, and these two protons means these two ortho proton of this methyl group is the number first proton, number second proton. These two proton it gives doublet at 7.4 ppm, and the protons adjacent to this nitro group means these two protons it gives signal at 8.2 ppm, means at a downfield region due to more electronegative nature of this NO2 group. These are the problem number 4. Then this is last example. Using H1 NMR spectrum, determine the structure of an unknown compound X that has molecular formula C4H8O2 and contains CO absorption in the IR spectrum. It gives significant absorption in the range of 1700 centimeter inverse to 1845 centimeter inverse due to presence of this CO group. In NMR, it gives three signal. Number first, triplet at 1.1 ppm, quartet at 2.3 ppm, and singlet at 3.7 ppm. And the integration value of these three peaks is a 15, 11, and 14. Means in H1 NMR spectrum, it gives these three signals. Okay. Number first step, to determine the number of different kinds of proton. So basically the number of NMR signals are equal to the number of different kinds of protons. Basically in this example there is a three types of signal, means there is a three types of proton A, B, and C, and these three types of protons are non-equivalent. Okay. Then step second, use the integration data to determine the number of hydrogen atoms giving rise to each signal. So basically the total number of integration unit for these three signals is 14, 11, and finally 15, means there is a total 40 units. It is the total number of proton, 8 proton. Molecular formula C4H8 means there is 8 proton, means 40 divided by 8 means finally 5 units per proton. And the calculate number of proton in each signal. The integration value for the first signal is 15 divided by 5, means there is a 3 protons. These 3 protons it gives triplet. 11 divided by 5 means 2.2 is a near about 2, means this 2 proton it gives quartet, and the last one is 14 divided by 5 means 2.8 is a near about 3, means this 3 proton it gives 1 singlet. The next one is a calculate index of hydrogen deficiency by using same formula 2x plus 2 minus y divided by 2. Number of carbon 4, number of hydrogen again 4, then index of hydrogen deficiency, number of carbon 4, number of hydrogen 8, the index of hydrogen deficiency 2 into 4 plus 2 minus 8 divided by 2, answer is 1, means there is only one unsaturation, and this one unsaturation is a carbonyl group C double bond O. Then step second, use individual splitting pattern to determine what carbon atoms are bonded to each other. Start with the singlet. Signal C means singlet is due to methyl group which is no adjacent non-equivalent, means there is no adjacent non-equivalent proton, and the structure, possible structure, this methyl group is either directly bonded to more electronegative oxygen, or this methyl group is directly bonded to carbonyl carbon. Number second, the simple signal A means triplet is due to 2 hydrogen, means triplet is due to 3 hydrogen, means there is a 2 adjacent methyl group, is according to splitting pattern 2 plus 1 is equal to 3, means this 3 proton it gives triplet. Then because number B signal means there is a quartet of 2 proton, means this 2 proton adjacent with another 3 proton, means there is a CS2 CS3 unit, CS3 it gives triplet and CS2 it gives quartet, means the fragment is a CS2 CS3. Okay, and from above data, it is the final structure of this molecule is either first or second. Okay, but correct structure is a number first structure, because there is a 3 signal, number 1 triplet, then quartet, and last one is the singlet. Consider the number third signal singlet at 3.7 ppm, and the singlet at 3.7 ppm due to 3 proton, means methyl group is directly bonded to more electronegative oxygen. Due to more electronegative nature of this oxygen, it gives signal at a highly downfield region. But in case of first, means this methyl group is directly bonded to this oxygen, but in case of second structure, this methyl group is directly bonded to carbonyl carbon, means it gives absorption, means it gives signal around 2.1 to 2.2, means structure 1 is a correct structure. This methyl group it gives singlet at simply 3.7 ppm. Out of these two structure first, structure A is a correct structure. Friends, the references used for this presentation is a simple spectroscopy by P.S. Kalsi, then pathways in organic chemistry, Saujanya publication, and finally thank you very much for listening.